A new era in analog design begins here. Our project, Neural Network-Based Offset Calibration using Capacitor Arrays in Dynamic Comparators, integrates intelligence with precision at the circuit level. This work was mentored by Dr. Anil Singh and Dr. Alpana Agarwal. I'm Angel Garg, a third-year electronics engineering student specializing in VLSI design and technology. I'm passionate about merging artificial intelligence with analog circuit design to create smarter, self-correcting hardware systems. A quest for precision. From massive AI data centers to 5G networks, modern systems demand incredible speed and flawless accuracy. At the core of these high-speed decisions is the comparator, a digital switch that converts tiny analog voltage differences into instant, yes or no, decisions. Comparators are essential building blocks in high-speed ADCs, biomedical devices, communication networks, and advanced power management. But there's a key challenge: offset voltage. This is a small, inherent voltage difference that prevents the comparator from perfectly balancing at a zero input. Even tiny offsets can cause significant errors in high-speed applications, making correction critical. Our novel solution: we've integrated AI directly into analog hardware, creating a self-calibrating comparator that instantly corrects its own errors while operating at 1 GHz. This is a three-part system working in harmony. First, the sensor, a time-to-digital converter, or TDC, measures timing errors in the time domain, which are directly linked to the voltage offsets. By carefully scaling the TDC and capacitor array, we can push these corrections into the sub-microvolt range. Next, the brain, our custom neural network, calculates the precise correction needed based on the timing measurements from the TDC. Finally, the action, a capacitor array, in a single step, injects the exact counterforce to restore perfect comparator balance. Simulation and methodology. We've successfully demonstrated our proposed methodology through extensive simulation in a working model. The core of our system uses a 3-bit TDC to capture the timing information. Our simulation was conducted using a 180 nanometers tech node with a 1.8 volts supply voltage. We tested it across a temperature range of -40 degrees Celsius to 25 degrees Celsius and used a ramp slope of 0.9 V. The system operates at a high clock frequency of 1 GHz. Core circuit components. The central component of our design is the strong-arm latch comparator. It's a high-speed dynamic comparator that uses a positive feedback latch to amplify small input differences into full-scale digital outputs. To ensure a clean, smooth digital output, we've attached an SR latch to the comparator. This is crucial for eliminating any glitches or unwanted states, providing a stable output that can be reliably used by the rest of the system. The time-to-digital converter. The time-to-digital converter, or TDC, is the key component that translates the comparator's small timing errors into a digital code. It works by measuring the time delay between the comparator's decision and a reference clock edge. This time delay is a direct and linear representation of the comparator's input offset voltage. A limitation of our current project is the number of bits in the TDC. As we increase the number of TDC bits, we can map the offset range with greater precision, allowing for more granular corrections and even better performance. This is a key area for future improvement. Neural network training. This is where the intelligence comes in. The neural network's training process began by generating a robust dataset using Monte Carlo simulations on our circuit. These simulations accounted for variations in manufacturing, providing a wide range of offset values. The network was trained to classify these offsets and map them to the correct correction code. The final, trained neural network is a compact model that can be directly implemented in hardware. For our 3-bit TDC, the mapping is represented by this logical truth table, showing how a given timing error is translated into a precise correction command. Results and conclusion. Our simulations validate the effectiveness of this approach. As you can see from the Monte Carlo simulation results for 250 samples, our method successfully reduced the average offset from an initial 39 mV to just 7 mV. The impact is clearly visible in this graph of the Gaussian distribution. The wide, uncalibrated distribution of offsets on the left is dramatically narrowed and centered on zero after calibration, demonstrating a significant improvement in precision. The future of analog design. This project represents a step forward in the evolution of analog design. We're moving from a time of manual tuning and lengthy iterative adjustments to an era of adaptive neural networks, where components can correct themselves. This is a critical foundation for component-level AI that will ultimately lead to fully automated hardware, smarter, faster, and more precise than ever before. Thank you.